There are 3 people in one camera. So we lost the Wi-Fi in the institute. So some people went home. So some people will be watching from home and some from here. We are in a new room. So, okay. I think we can slowly start. Welcome back, everyone. Today we have Marco Armenta, and he's going to tell us about representation theory of neural networks. Take it away, Marco.
Thank you. Well, thanks for the invitation. It's really nice to give a talk here. So yeah, I'm gonna tell you about some applications. First, small warning. This is not a talk on representation theory. This is a talk on applications of representation theory to neural networks. So, but since this is like a joint work between the two worlds, I'm going to repeat myself a couple of times in the two languages. So sometimes I'm going to say something that you will not understand because you are a representation theorist, but I will going to repeat that in the language of representation theory. And the same thing goes for deep learning. So yeah, well, I'm a mathematician by formation. I'm a representation theorist, but then I moved to do some applications in neural networks. And right now I'm a quantum software developer at the Institut Quantique here at the University of Sherbrooke. So, and I'm going to talk to you about some applications here that I've been working with Pierre-Marc Jodoin and more people. So let's get started. So let me tell you first, what can neural networks do? So they can do a lot of things right now. So some of the things is object recognition and image and object classification. So for example, you put an image or a video and you can tell using a neural network where are each object and what type of objects you have there. You can also do segmentation, which is basically you classify each pixel in your image belonging to different classes. They can play chess. They can play Go better than humans, better than any human. And lately, they can also do protein folding. So this is just one of the few things that they can do. They can actually do a lot of things. And how? How do they do this? Well, you need a couple of things. You need lots of data. You need labeled data, unlabeled data, or generated data. You need also lots of computations. You have to do the training on several GPUs or TPUs, whatever that means. And you also need a good loss function. So once you have all these three things, you run the algorithm and it somehow converges to something that has all these magical properties. So, and apparently the bigger the network, the better. And we don't know why. We have some ideas, but we don't know why. And lately we have these things called transformers. Some examples of it, these are just very big neural networks. And you combine certain things. There's the notion of attention. There's the notion of, you parallelize all these computations. And this, you have, for example, this model GPT-3, which is a language model, which means it interacts via text with you, or it does things that you tell it to do, or you don't even have to tell it what to do. And sometimes it even does what you expect it to do. This DALI, this is a generative model. You give it a description of something and it generates image like that. So for example, you say avocado shaped furniture, and it generates furniture with the shape of avocados. So, and you can Google these things and you can see a lot of descriptions about this. So, but we don't know why neural networks work or fail, and that's a problem. Because Moore's law will hold for at least 10 years more, which means we will be able to construct even bigger neural networks. And we have some problems with today's neural networks. For example, we have adversarial examples. This means, let's say you train your neural network and you put it in your self-driving car. So, and you find a stop sign. Now, this should be classified as a stop sign because your car should stop there. But an adversarial example It's an image that looks like a stop sign, but actually you add some carefully crafted noise. And to you as a human, this still looks like a stop sign. Actually, you can do this so that a human cannot notice the addition of noise here. So you see exactly the same image. I'm just adding some noise here so you can see this different image. But your self-driving car will say, hey, this is a 100 kilometers per hour sign, so I should accelerate there. So as you can see, this is a huge problem. We also have catastrophic forgetting. Let's say you train your neural network to do something like distinguish between stop signs and 100 kilometers per hour signs, and you want it to do other things like, I don't know, classify handwritten digits. But if you do that, then you forget what it has learned previously. And we don't know how to solve this. We also have the hyperparameter search. So before you train your neural network, you have your data, you have your neural network, you have your loss function. And there are some parameters there that you have to fix manually before the training. And you don't know what's going to happen after the training when you do this. So you have to run the training with these hyperparameters. Now, if you change one of those parameters just by a little bit, you will end up with a neural network that is going to have a different performance, sometimes better, sometimes worse. And you don't know which choice of hyperparameters is the best. So what you have to do right now is you have to train with a lot of different hyperparameters, save all the results, and then pick the one with the best performance. So, and this is why you need forests of GPUs. This is why you need a lot of computations. So, and there's also this thing called generalizations, which is basically you take your big data set and you take a part of the data and you put it aside and you train with the rest of it. And at the end, you test the performance on the data that you put aside. And somehow neural networks behave really good on the data that it hasn't seen before. And we don't know why this happens. Now, it's true that I'm saying that we don't understand what's happening here, but we have some tricks, but these are really just tricks. Like, okay, we've done some analysis, some empirical analysis, some experimentation. And it turns out that, for example, if you do learning rate over the batch size, and that more or less controls generalization, but then you change the data set, you change the neural network, and it is not true anymore. So we have tricks, but we don't have a rigorous analysis of what's happening here with all of these things. And we probably won't solve these problems if we don't understand what the computations of neural networks are doing. And now let me tell you about our approach to neural networks. What we want is we want to account for all the computations of a neural network. And we also want to account for the structure of the operations. This is in terms of the underlying graph or the underlying quiver of the neural network. And of course, this requires a different type of mathematics that has not been used before to study neural networks. And these are quiver representations. Because what we want is a precise mathematical description of the computations that neural networks are performing. Okay, so let me get started with this picture. So you all know what I'm doing here. This is just a matrix multiplication. But actually, you can rearrange this into a neural network layer. So you have your input, x1, x2. Then you have your aij's, which was a matrix, but you can arrange it in terms of a quiver like this. And at the end, what you do is you multiply this x1 times a11, and x2 times a12, and then you add the results. And also for the other vertex here or the other neuron. Now, this thing here, every time you use the aij, you use it as a multiplication by it. So it's not, this thing that you're looking at, this is not a weighted oriented graph. You are actually assigning a linear map to every edge here. And this is, by definition, a quiver representation. Okay, but probably people from deep learning should be complaining right now because where's the nonlinearity? There's one thing that I'm not telling you yet, which is how to deal with the nonlinearity. So what is this? Let's say we're looking only at these two arrows and you plug in your input there. Now this gives you this addition of these two terms. Then you have to apply a function f. Now this function should be nonlinear and it's called an activation function. And you have to apply this every time after you apply a matrix. So you apply a matrix and then a nonlinearity. Actually, you do this pointwise. And this is how you construct a neural network. You apply a linear map and then pointwise nonlinearity. If f is a linear map, your neural network would not learn anything. So you need f to be nonlinear. So, and you can extend the quiver. So you add more layers to the quiver. So let's say we have another one here, and the algorithm looks like this. So you apply first your matrix, then the pointwise nonlinearity. And I'm going to relabel this just to save notation. And this is the new values on these vertices. And you apply the algorithm again, but now on this on the next layer. So you have these values, then you apply this matrix or this quiver representation, and that's it. So for this particular example, we have defined a function which takes an x1, x2, a two-dimensional vector, to another two-dimensional vector that you're looking here. And again, the algorithm is a matrix, then pointwise nonlinearity, then a matrix, and so on and so forth. And this is called the network function of the neural network, which is the input to output function. Okay, now let me make a warning here, because in machine learning, when you say neural network, people usually understand network function, and they make no distinction between these two things. But we will make a distinction between a neural network and its network function. For us, these are two different things. So yeah, and I've been talking about, this is going to be my running example because I'm going to do some computations on it and with it. But actually, this works for any type of neural network architecture. In general, you have these big models, and they can have convolutional layers. They can have batch normalization layers, pooling layers, fully connected layers, so on and so forth, different kind of activation functions. But it's always a cyclic quiver. So an oriented graph without cycles. Now, there are some things here. For example, recurrent neural networks, they draw them like cycles, but these are not actual cycles like we see in representation theory. These are finite cycles. So let's say we have this quiver for the neural network. And let's say we have the sources or the inputs, and we have k sinks or k output neurons. Now I'm going to denote by W. This is going to be the thin quiver representation of the neural network. And this is what we call the weights of the neural network. F is going to be the activation function, which again is nonlinear. And my neural networks are going to look like this. My neural networks are pairs of a thin quiver representation and an activation function. Now, how does the neural network makes a decision on an input? Well, you take an input X, you plug it in here, and you evaluate the network function that I'm going to denote by psi of WF. Now, this is a map from R to the D to R to the K. And when you evaluate this on X, you get a k-dimensional vector, and the decision is the pre-assigned label of the entry with maximum value on this vector. So for example, let me go back to our running example. So let's say we train this neural network to distinguish between stop signs and 100 kilometers per hour signs. So the first output here is going to correspond to the stop signs, and the other to the 100 kilometers per hour signs. So if when you run the algorithm of the network function, you end up with a two-dimensional vector. If you have a maximum value on the first entry, then it's a stop sign. Or you say that the neural network is making the decision that this is a stop sign. And the same thing for the other output vertex. Now, I'm not telling you something else here. Here you usually apply something called a softmax, which gives you some interpretation of these values on probabilities. But it's the decision is the same. But in deep learning, you put the softmax because you want to have a notion of a notion of probabilities that the neural network is assigning probabilities to each class. But the decision is going to be the same here. So we have the network function that it's a map from R to the D to R to the K. Now, okay, so in representation theory, we usually like to work over algebraically closed fields, and we do that. But for neural networks, what we do is we make all the constructions on complex numbers, and then we restrict to the real locus. So, and the first theorem that we proved, this is a joint work with Pierre-Marc Jodoin, is that you can factorize the network function like this. And this means factorization means as a composition of functions. And this space M, this is a moduli space of double frame thin quiver representations. Now, this is a mouthful, but what it means is that every point in M, it's a weighted oriented graph, and the graph is the same as the graph of your neural network. But there's no non-linearities in this space M. These are just linear objects. Okay, so now I'm going to describe to you what happens in each part of this map, of this diagram. So I'm going to describe first this map, but I'm going to restrict myself to our running example. So I have this neural network, WF. My weights are the AIJs and the BIJs. And now this map, phi WF, is going to take an input vector in R squared, and is going to produce one point in this moduli space. And the points in this moduli space are weighted oriented graphs. So I need to define, given an input, a weighted oriented graph. And I'm going to do it like this. So remember that this is an input vector. This is data that you have. And what you do is this. So I'm going to ignore first the layers on the right. And I'm going to work first with the first layer. And I'm going to do this. So what happened here? The x1 was in the first neuron here. And I'm going to multiply all the weights that start in this same neuron by x1. And the same thing happened in the other. So you do this for all your input neurons and on the first layer of arrows here. Now, once you do this, oh, sorry, I don't know what's happening. Okay. So now I'm going to compute. I'm going to look at the steps of the forward pass. This means I'm going to look at everything I compute when I define the network function. But I'm not going to compute the network function. So this F1 is the activation on this first neuron. F2 is the activation on the other neuron. But I'm also going to need the pre-activations, so the values after applying the first linear map. And I'm going to denote them like this, and then I'm going to take the quotient. So I'm going to do for each hidden neuron activation over pre-activation. And then I'm going to do the same thing I did before, but for this next layer. So I'm going to consider this as values on these neurons, and then I'm going to plug the values on the weights. And you can see that what's happening here is the values that I used to have here, which was f1x over f1 hat of x, is going to multiply all the weights on the arrows that start on this vertex. And the same thing happened with the other. So this is very algorithmically what's happening. And this is the value of this function phi WF on an input x. Now, representation theorists can notice that I'm putting here isomorphism class because points in the moduli space are isomorphism classes of double frame thin quiver representations. So this is how you define this map. And we know a couple of things about this map. First is that all neuron values, which are the activations and pre-activations, can be obtained from this map. And these activation values of neuron, this is what you call in deep learning, this is what you call a representation. So every time I'm saying representation here, I mean a quiver representation, not in the sense of deep learning. And you can recover from this map all the representations that you understand in deep learning. And you can also recover the output of the neural network. And moreover, this map also encodes the order of the operations in terms of the underlying quiver of the neural network. So we're actually accounting for all the computations of the network in this language. And this is another theorem that we have. This is joint work with Thomas Brussel, Suheila Hassan, and Marcus Reinecke. And is that we can also recover the gradient of the neural network from this map. So every building block of neural networks is encoded in this map together with all the computations. And this is independently of the task, independently of the data, independently of the architecture of the network. So this is really a universal description of neural networks. All right, so let me go back to this diagram that we have. So I described to you the bottom left map and the bottom right map. You can see I'm not making this psi hat does not have a reference on the neural network because it does not depend on the neural network. And the neural network in terms of the weights and the activation function. But it depends only on the structure of the quiver, only on the combinatorial structure. So let me now describe this map. So this space M, this moduli space, the points here are weighted oriented graphs, which have the same graph as your neural network. So let's say I take this isomorphism class in the moduli space, this weighted oriented graph, and I want to evaluate this psi hat here. Now here, okay, so I'm using the same one, the image of the point X under the map phi WF, but you can see this as a general quiver representation, thin quiver representation. And what you do is you apply the network function to this graph as if you don't have nonlinearities. So this is just a sequence of linear maps. And you do it always on the same input vector, the input vector with only ones. So you propagate this and you obtain some values, y1, y2. So these are just applying these matrices. And this is how you evaluate this psi hat. So you take your weighted oriented graph, your double frame thin quiver representation, you evaluate the network function on the vector with only ones, and that gives you this output, y1, y2. So this is the description of this diagram here. Now, what I want to do now is I want to explain to you what's happening to the training when you look at this picture. So first, I'm going to make a drawing. It's not going to be a precise drawing. And I'm going to change the input space to RD because I want to consider images. So I'm going to draw this moduli space M as a sphere, but it's not a sphere. Okay, it's a very high dimensional object. And now if we only look at this map psi hat, this produces a partition of the moduli space in terms of the decisions of the neural network. So if we're doing, in this case, binary classification, let's say I'm focusing to distinguish between stop signs and 100 kilometers per hour signs, then you look at the thin quiver representations that when you evaluate the vector with only ones, then you get the maximum value on the first output neuron or the first sink. And that gives you one partition there. And the other part corresponds to the dual thing. So the output, the quiver representations that have the output with the maximum value on the second entry. So I'm drawing this just as a partition on this sphere. And so the North Pole in this case corresponds to the stop signs, and the South Pole corresponds to the 100 kilometers per hour signs. And so what does this mean? This means that once we produce this partition, we have translated completely the classification problem to this map. So I only need to look at this map and the partition of the moduli space to understand what's happening during training. So let's say I have my data here. So the red dots, these are stop signs. These are actual stop signs. And the black dots, these are 100 kilometers per hour signs. And I'm going to map all of them with this phi WF to the moduli space. But first, you initialize the training with this W chosen to be random. That means every weight here, every value on the thin quiver representation is chosen randomly. So that means you have a random distribution inside the moduli space. And now you're going to produce via gradient descent a sequence of thin quiver representations of these W's. So I'm starting now at epoch 0. This is times 0 on your training. And then you produce the next one, and this changes the configuration of the points inside the moduli space. And you keep doing this, points get rearranged, epoch 3. And finally, let's say you go up to epoch 100, and then the picture looks like this. And this is exactly what's happening during training. So your points get rearranged, and on a classification task, each point corresponding to each class goes to the right side on the moduli space. So now, this picture accounts for all the computations of the neural network and the underlying quiver of the neural network. And we also have a nice algebraic description of this map. When you evaluate this on an X, this is a tensor product of quiver representations. So the first part, this is a neural network. This is the neural network weights. And the part on the right, this depends on the data, on the thin quiver representation W, and on the nonlinearity. So this TXWF accounts for all the processing of the data inside the neural network. And this thing in the middle, this is a tensor product of quiver representations. So let me look now at adversarial examples. So once we partition the moduli space and once we train the neural network, this should behave really good when we look at the real world data. And it's usually the case, except for adversarial examples. So let's say I have a new data, new stop sign that I didn't look at during the training. Now this is going to be classified as a stop sign. So it's classified correctly. Now, so good, so forth. But now, let's say I have a new data sample. Oh, sorry, let's say I have the same data sample, but I add some carefully crafted noise. So this is adversarial noise. I'm changing a few values on the pixels. This is going to give me a different point in the input space. And I can produce this so that it's really close to X. So, and I can put here almost any epsilon, and I can produce this X prime that actually looks like a stop sign. But when I apply this phi WF, it goes to the other side of the decision boundary in the moduli space. So, and this is exactly what's happening to adversarial examples. Now, I'm not going to tell you how to detect adversarial examples, because I don't know how to do it, but we know that this is what's happening inside the moduli space. So
can I ask a question?
Yes, please do.
What's the metric here? So what's this P norm?
Yes, this is a P norm. You can actually do this with several P's.
So this is the usual, the norm in the R to the D.
Yes, this is a distance. This is a norm in R to the D.
Okay, thank you.
Yes. Okay, so yes. So now let me look at something else. This is called the manifold hypothesis. So there's one thing in deep learning is that we try to understand what's happening to the data. And what you do is you assume that the data lies near a low dimensional manifold inside R to the D. So let's say, for example, we have this stop sign manifold in R to the D, and you map this into the moduli space now. So we are trying to understand what's happening during the training to this manifold inside the moduli space. This is a work in progress with Alexander Schmidt. And what we're trying to do is, can we say something else? Because right now, all we do is we analyze the values of the neurons layer by layer. But if you do this, then you can, again, you can get some tricks like to help you during training, to help you make better decisions for your neural network. But again, these are just tricks. We don't have a clear mathematical description of what's happening. But here we can map this data manifold inside the moduli space. So we are trying to understand what's happening to the geometry of this data manifold. So what else can we do? Well, apparently we can apply isomorphisms of quiver representations to neural networks. And we try to do this during training. So I'm going to show you now some training curves. But first, let me tell you what's happening here. So tau, it's an isomorphism of thin quiver representations, actually double frame thin quiver representations. And you can apply this to W without problems. But to the F, you have to consider F as loops inside the quiver. And remember that F is nonlinear, but you can still apply this change of basis. So you end up with a new neural network that has different weights and different activation functions. And again, this is a joint work with Permat-Jodoin. Is that in this case, in the case of isomorphic neural networks, you have the exact same network function. So you have two very different neural networks with the same underlying graph, but they compute the same thing. And we tried applying random isomorphisms during training. And we call this neural teleportation because basically, if you look at the deep learning description of this, you have a landscape and you're trying to climb down the landscape during training, but this applying one isomorphism takes you to a different landscape and you have the same network function. So here we have some training curves. Let me explain this to the representation theories, probably for deep learning expert, this is very clear what's happening. So on the x-axis, we have training time. So this is the sequence of thin quiver representations during the training. And on the y-axis, we have validation accuracy. This means this is data that we are not using for the optimization that we put aside. So we are looking at the performance of the neural network during the training on data that we're not using for the training. So as you can see, this is increasing with respect to time. And now here, the orange line, this is the usual training of your neural network. We're not doing anything here. But the blue one, we apply one random isomorphism, one teleportation at epoch 30. So at the 30th element in the sequence, we apply a random isomorphism. And somehow we see a better performance. So we are changing this WF. That means we are changing the map into the moduli space, but the network function is exactly the same. But somehow the training is better when you do this. And we have some values that control how large is this change of basis, this isomorphism. We choose it, basically we put two Gaussian distributions around -1 and 1, and we sample randomly for each hidden neuron. And then we can control the width of these two Gaussian distributions. And this is the change of basis range that you're looking at. So if we put 0.7, then we see some increase on the validation accuracy here. And if we increase that up to 0.9, you can see that this somehow corresponds to how better the training is going to be. So yeah, and I mean, this is pretty weird. We cannot prove that this is going to happen and why this happens. We have a lot of experiments, and this seems to be like systematic. We have actually, these are two really big neural networks. This is a VGG, this is a convolutional neural network. And this dense net, it has a lot of convolutions and batch norm and something called dense connections, which means you put arrows that jump across layers in your quiver, and you don't compute gradients on those arrows. So you only make the training on the other part of the quiver.
So here, the
yes.
teleport is done randomly. You choose the isomorphism class randomly. Is that right?
Yes.
Oh, that's okay. So a random choice gives you a better performance.
Yes.
Wow. Okay. Thank you.
Yeah, and I mean, again, we don't have a proof for this, but the idea is that what you are changing here is the map that injects the input space into the moduli space. This is the only thing that we can say for these things. And I mean, we can also compute the gradient of teleportation. And well, it's different, but this was already known. The only thing that we're changing here that is different is that we can change the activation function, and this works for any activation function. Okay, so that's it. So let me give you the take-home messages from this talk, and is that we have a new way of representing neural networks. And with this new way, we can account for all the computations of the network. And we also account for the order of the computations in terms of the underlying quiver of the neural network. And we can also describe the training dynamics inside the moduli space using this new language. And we can apply isomorphisms of quiver representations to neural networks, and somehow this seems to help. So that's it. Thank you very much. And I'll leave you with some references on this.
Thank you very much. Let's thank Marco for this nice talk. I will first ask people in the room if they have questions. Any questions from the room? Bethany?
Can you hear me?
Yes.
Okay, great. Is it possible that different quivers might have the same function, same neural function?
I will say no, but I don't have a proof for that. But well, actually, there's work by Jordan and Robin Walters, and they're doing some reduction on the size of the quiver, and you end up with the same network function. This is again, I'm sorry, I don't have the right reference for that, but I can send it to you. I have it saved somewhere. But yeah, you can do this. You can somehow reduce the size of the layers, and you end up with the same network function.
Okay, great, thank you.
I see someone in the chat. Yuri, do you want to ask your question?
Yes, thank you so much. Can you hear me and can you see me?
Yes.
Okay, thank you very much for the talk. It was very interesting. So I'm not an algebraist. I'm rather an applied analyst. So forgive me if I didn't understand something, but so it seems that you looked at large and complicated neural networks, and then just shown how to describe all the computations that networks do in the language of representation theory. I was wondering if you have looked at something much more simple, at neural networks with just one hidden layer. So you have your input, you map it somewhere, then you apply a nonlinearity, and you map it to the output. It's much more and much that we have a much better understanding of these networks from the point of view of functional analysis. So I was wondering, and we have also, so you can represent these networks using Radon measures on some on a compact parameter space. And then you also have these equivalents of, so you have these equivalence classes of various sort of realizations of a network that actually that in fact give you the same mapping. So there seem to be some parallels there, at least in that simple case where we sort of understand more on the analytics side. I was wondering if you have thought about it, and maybe if you hadn't, I was wondering if you think this would be sort of fruitful to see how the analysis and the algebra sort of play together.
Yes, actually, this is what we are doing right now. So we are looking at the one hidden layer only, and we're trying to study this on small examples, but this is still work in progress. We still don't have a clear description of what's happening here, but we are working on it.
Okay, thank you so much.
If you're interested, send me a message, we can discuss.
Sure, thank you. I do have another question, but I probably should let other people ask first.
So are there any questions from the room? I don't see any in the room. You can go ahead and ask your second.
Okay, thank you. So my other question is, in your first mapping that takes you to the moduli space, you have this fraction of basically the output of a layer after you applied the nonlinearity, and you divide it by the output before applying the nonlinearity.
Mm-hmm.
So everything before the division you can generalize pretty well to arbitrary spaces and everything. So you can just consider maps between Banach spaces, and the nonlinearity would be some function on the Banach space, etc. Blah blah blah. But in the division, you will be struggling to define. Is there another way of writing this?
No, actually, this diagram. Let me come back to it. This diagram that we built. What I wanted to do is I wanted to get rid of the nonlinearity, because I wanted to describe everything as quiver representations. So,
Sure.
and as you can see, I'm putting everything that has to do with the neural network on the left-hand side. And on the right-hand side, I have something that only depends on the underlying quiver.
Sure, sure.
And
but then at a later, in one of the later slides, you constructed a sort of a concrete example of this phi, if I understood you correctly.
yes,
And then
there.
yes, and then you have these fractions f2 of x over f hat 2 of x.
Yeah.
So this f2 of x would be the output after applying the nonlinearity, and f2 hat the output before applying the nonlinearity. Did I understand you correctly?
Yes.
Okay. So is this taking this fraction? Is it just an example, or is it something that you prove?
No, actually, this is the thing that you have to do if you want to construct this diagram.
Okay.
Is the only thing that works.
Okay. So I was wondering if now these f's actually take you into some Banach space, and then you can define f2 or f2 hat, and you can define f2, but then there is no division. So how would you do that if you want to take it to, if you were to go away from RD and from these pointwise things? How would you do that then?
Yes, that's the thing, because when you try to write down the computations in these terms, you have to forget about this computation of layer by layer. So because when you look at this diagram here, so the network function, you usually understand it as first layer, then nonlinearity, then the next layer, nonlinearity, next layer, nonlinearity. But all this algorithm from the beginning to the end is described by this diagram. So you don't have a notion of what's happening on layer by layer. But this map C hat, you can consider it composed with something that we call a forgetful functor, which means you have your whole quiver and you forget some layers. So you drop some layers on your quiver, and then you apply the corresponding C hat, and that gives you the values on the hidden neurons. So you can recover the representations in deep learning from these representations, from these quiver representations. So we haven't looked at how this behaves with the notions of what's happening in terms of, because I think there's also one notion that if you use ReLU activations, you can understand this as with the tropical geometry point of view. I don't know if you've seen this.
No.
But this is very specific to ReLU activations.
Okay. Well, you can also understand the ReLU in terms of partially ordered spaces. So it's it's the lattice operation of taking a positive part of element.
Yes, yes, exactly.
Thomas has a comment. Thomas, you can go ahead.
Sorry?
Hello, can you hear me?
Yes.
I'd like to add a little comment there. This division by those scalars in every point, this comes basically from the notion of isomorphism of quivers. You have to do that. And so strictly speaking, you don't want to divide by 0, obviously. So the map phi is only defined on an open subspace, an open subvariety of RD, right? Where,
Yes.
where the iterated process doesn't give you zero, so you never divide by zero. However, you can consider activation functions that whose values are always strictly positive, and then you don't have a problem.
Mm-hmm. Sure. Yeah. Actually, what I meant is that you take that your input space is not R2 but some Banach space, and then the output space is also not not RD or IK, but just two different Banach spaces, and then you don't have these pointwise things. But then I understand that the sort of the layer by layer picture goes away anyway, so it's probably a different thing altogether. I wonder if you thought about generalizing it to input-output spaces that are not Euclidean.
Yeah, I mean, you can still consider the layer spaces, but you have to do this thing that I told you, that you have to consider this forgetful functor, and you compose your psi hat with this forgetful functor, and that gives you the map into one of the hidden layers. Mm-hmm. So you can do that. This is still, although you're forgetting about the layer by layer computations, you can still recover that information. Mm-hmm. But we haven't looked at how it behaves in terms of, if you consider, for example, the hidden space as a Banach space, and then you look at what's happening inside there. We haven't looked into that.
Mm-hmm. Okay, thank you so much.
And Marco, I have another question about maybe one question about the representation theory. How bad does it get? I mean, you have this extremely big quiver, which is wild, but you just consider thin representations. So how bad is the representation theory that is involved?
I think this, for the majority of for the majority of quivers that you use in deep learning, for this dimension vector, the representation theory is wild. So that's why you can construct the moduli space, because it's a wild representation type.
Do you allow parallel error?
No.
But the moduli spaces are pretty bad. They have singularities and everything.
Yes, this is actually on the last paper that I mentioned. We study what's happening there. These double frame moduli spaces of quiver representations. We showed that this space is highly singular, but we have a resolution of singularities.
Any other questions or comments?
Could I ask a question?
Yes.
Hey, Marco. So could you go to the slide about the adversarial example?
You mean this one?
Yeah. So does this mean that this map phi is somehow discontinuous?
No, actually, what I think is happening, that, I mean, we're still trying to look at what's happening here with Alexander Smith, is that this P ball, this P neighborhood around your X, it's stretching a lot here. Yeah, we're not claiming it's discontinuous, but somehow it also has to do with how all the points are mapped. Because if you can construct adversarial examples, that means that either something weird is happening to this phi, or all the points are mapped close to the decision boundary somehow. And we know this because adversarial examples exist.
Okay, thanks.
So I have a quick question. Do you have a metric on the moduli space?
What, sorry?
Do you have a metric? How do you measure the closeness in the moduli space?
Yes, we're also trying to do that because in the moduli space, you have all these quiver representations, and apparently we can represent each point there by the matrix. So you multiply all these matrices, and it gives you one matrix of number of input neurons by number of output neurons. And this matrix represents all the, you can recover the output of the network from it. So that means you can understand each point here as a matrix. So in principle, we can use the metric for matrices. But we still don't know which matrix is the one that's going to give us the right description that we want.
So the gradient descent is done on R to the D, not on the moduli space, right?
Yeah, actually, well, when you do gradient descent, actually what you do is a stochastic gradient descent. You compute the gradient with respect to some points in the moduli space. So what you're doing is, if you think about it in terms of the manifold hypothesis, then you're mapping your manifold to the moduli space, and then you have some gradients there. And what you do is you use some average, and then you follow that inside the moduli space. So you can do you can try to understand the gradient descent inside the moduli space.
Mm.
Yeah, but I've been trying to rewrite the equations of gradient descent here, but I'm pretty bad with differential equations, so that might take a while.
I see. Okay. Thank you.
Thank you. Just a quick follow-up on that. In the case of these simple neural networks with one hidden layer, there are papers that show that the gradient descent in the parameter space, so in R, whatever the number of your neurons is, it actually corresponds to a metric gradient descent in the space of radon measures on that parameter space. So it's a gradient descent with respect to the Wasserstein metric. So I was wondering if it was similar to your representation here, where maybe this moduli space would be somehow related to the space of radon measures on the parameter space of the neural network, and maybe then the gradient descent in RD would correspond to a certain type of gradient descent in the moduli space. I don't know if there is such a connection, or maybe it's a different.
No, we haven't looked into that, but it sounds interesting. I don't know, maybe I can ask you for references on that.
Sure, I can send you some papers.
Yes, please.
Thank you.
Thank you.
Thank you very much all for these nice questions. Let's thank Marco again.